Welcome back to the Quantum Rings Quantum Summer School. Last week we talked about noise and error mitigation. So we know that our qubits are not perfect and we have a long ways to go to getting to fully error-corrected, fault-tolerant quantum computing. Today we're going to be talking about something that we can do in our NISQ-era, Noisy Intermediate Scale Quantum, and that's variational algorithms. Today we're going to be talking about the Variational Quantum Eigensolver, and next week we're going to be talking about the Quantum Approximate Optimization Algorithm. Let's get into it. So today we're going to start off by talking about Hamiltonians and ground states, and then we're going to move on to the Variational Quantum Eigensolver framework, and then some examples using VQE. So first off, what is a Hamiltonian? A Hamiltonian is a total energy operator of a quantum system, and it's super important. We can learn a lot from the Hamiltonian of a system. So there's two main things that we can learn from the Hamiltonian, and lots of other things too, but especially in the context of quantum computing and variation quantum eigensolvers, analog quantum simulation, digital quantum simulation. These are the two things that we care most about. So one is the ground state. The eigenvalues of the operator H, the Hamiltonian, are the eigenenergies of the system. And the lowest energy eigenvalue, the lowest energy eigenenergy, is the ground state energy. And just so you remember, if we have a Hamiltonian, an operator in general, the only possible measurement outcomes when you observe that observable are the eigenvalues. And then when you measure it, it collapses the state into that eigenstate, whichever one the eigenvalue that you measured was. And so this is just more mathy way of saying that our quantum systems are only allowed to exist at discrete energy levels. So it makes sense that a quantum system or any system will tend to settle into the ground state because it's the lowest energy state. And so that means that it's one of probably the most physically relevant state that a system is in. So we might want to know the ground state to be able to predict the behavior of certain materials. So from the ground state, we can learn something about the band gap of the material, its magnetic properties, electrical conductivity, those type of things. We can also learn about atomic and molecular stability. So if we have some atom or molecule, we want to know what's the equilibrium geometry, what are the bond strengths. And then also for thermodynamics, the ground state is the baseline for all the excited states. So we can also gain insights into that from the ground state. The other main reason that is helpful to know the Hamiltonian is for dynamics. So if you have a quantum system and you know its initial state, you want to know how it evolves with time. And that's governed by the Schrödinger equation. So you can see that here we have IH bar times the time derivative of our wave function is equal to the Hamiltonian times the wave function. So since we have this differential equation, if we know the Hamiltonian and we know the wave function at time 0, then you can find the wave function at any later time. And so this is the type of thing that we would do in the field of quantum simulation, where you're using a quantum computer as a tool to simulate a complex quantum system. But for today, we're just going to focus on the ground state physics, and that's where VQE comes in. So one of the main principles behind VQE is the variational principle. And there's a variational theorem which states that if H is a time-independent Hamiltonian and psi is an Ansatz is just a trial wave function. So you can think of it as a guess or like an arbitrary wave function. Then the expectation value of the Hamiltonian, which is going to be the expected energy, is always going to be greater than or equal to E0, which is the ground state energy. Now, this may seem perhaps a little bit obvious in the sense that how could a state have an energy lower than the lowest possible energy configuration? Doesn't seem possible, but let's just walk through the concept behind this and why it makes sense. So suppose you have your Hamiltonian, which has some eigenbasis, of psi n's such that the eigenvalues are ENs with E0 less than or equal to E1 less than or equal. So we can kind of sort them in ascending order in terms of energy. Then we know that since these psi n's form an eigenbasis, that we can express any arbitrary state, including our ansatz, as a linear combination of those eigenstates. So we can express our ansatz as some linear combination of them, where these Cn's are complex numbers. So now we can compute the expectation value of the Hamiltonian given this ansatz. And we can just plug in. Here I'm taking the dagger, so we're going to get Cn star, and this will become a bra H. And then the same thing over here using a different index. And then just distributing everything through. We have this Hamiltonian here acting on psi m, and psi m is an eigenstate with eigenvalue em. So we're going to get a factor of em, and then inner product of psi n and psi m. Now what's the inner product of psi n and psi m? Well, it should be 0 if n does not equal m, and it should be 1 if n equals m. So we can replace this actually with the Kronecker delta function. And just as a reminder, the delta function is 1 if n equals m, and 0 if n does not equal m. This is just because we have an orthonormal basis. So finally, anywhere where n does not equal m disappears, and we're left with this. Now we can pull out that ground state coefficient if we want to. And because our ansatz is normalized, we know that it ought to be the case that the sum of all the Cn squareds ought to be equal to 1. And so we could actually rewrite this as C0 squared plus sum over n greater than 0, Cn squared equals 1. So we can replace this here with 1 minus the sum over n greater than 0, Cn squared. And now if I just rearrange my terms and I bring that second part inside that other sum, we're left with this. And we know that En is greater than or equal to E0 for all n. So this is greater than or equal to 0, and we have that that expectation value is greater than or equal to E0. The goal of VQE is to try and get as close to possible to this minimum energy as we can. So our goal in VQE is we want to try to get our coefficient C0 as close as possible to 1 as we can, and all the other coefficients as close as possible to 0 as we can. We're basically trying to find this ground state eigenstate. And then we can do this by minimizing our expectation value of H. And hopefully this should approach E0. So now let's take a look at the algorithm as a whole. So this is going to be different from the other ones that we've seen before because now we have a quantum computer and a classical computer working in tandem. And we're going to go back and forth between the two, doing some iterative optimization. So we're going to have some parameterization, so some vector that we'll call theta, which could be just one number, or it could be a vector list of numbers. And we're going to use this to create our ansatz. So this part here, this U of theta, is a unitary that is going to prepare the ansatz given that theta. Then we're going to measure all the qubits for many shots. We want to build up some statistics. And then from that, we can compute the expectation of the Hamiltonian. Then we have our classical optimizer, which is going to take that, whatever the current theta is and the current expectation of h, and it's going to come up with a new guess for what theta should be. And then again, we're going to prepare that ansatz. We're going to measure many shots, compute expectation of h, and then find a new theta. And we keep going in this loop until eventually we meet some criteria or some like error threshold that we're okay with. And we say that that's the minimized expectation value of h, which should be approximately the ground state energy. So one thing I want to point out or emphasize here is that there's kind of two things. So first is that we're measuring many shots of this because we want to build up statistics for the expectation value. So for instance, if you have noisy quantum hardware, like we talked about last week, this might not necessarily be such a big problem because you can just take more shots and like build up more statistics. The other thing too is oftentimes we don't care about getting it perfectly. We care about getting close to some minimum. So that means that we don't need a perfect quantum computer in order to pull this off. It's okay if there's a bit flip here or there, because overall we're going to get approximately the right expectation values and be able to minimize to approximately the right ground state energy. So VQE is really nice because it can be used in this current period that we're in, which we call NISQ, noisy intermediate scale quantum computing, where we don't have logical error corrected qubits. The hardest part of this circuit is preparing the ansatz. And there's a lot of different ways that you could go about doing this, but generally there's two main ways. So the first is called efficient SU2. And SU2 is just the group of 2x2 unitary matrices with determinant 1. This is actually just the group of rotations on the sphere. So you can think of our Rx, Ry, and Rz rotations as making this SU2 group. And this is pretty hardware efficient, so we don't need to use that many gates, which means that the circuit depth is not that deep, and especially in our NISQ-era where we have noisy qubits, it's better to have a shorter circuit depth. We also need C-naughts, of course, because we need some way to have qubits interact and potentially entangle with each other. Otherwise, we just have like every qubit disconnected. So we definitely need at least one 2-qubit gate, which we use the C-naught. And so here's an example of how you might parameterize your unitary U of theta. So we have our vector theta, which has 13 elements in the way that I've drawn it. And we apply this sequence of gates with these thetas and the C-naughts where they are. And at the end, we get some wave function. And then we can compute the expectation value of h, and then use that to come up with a new theta. And then we would apply this unitary again to prepare the new ansatz, and we repeat this over and over again. You may notice here that we have a C-naught gate that goes between the first and third qubits. And sometimes things like that is not super practical because our qubit layout is constrained and we don't have all-to-all connectivity. You maybe only are connected. For instance, if you're in a square grid connected to your nearest neighbor, or if they're in a line, like in a square grid, they would have 4 nearest neighbors, in a line, 2 nearest neighbors. So in that case, you might want to use some 2-local method to prepare your ansatz. And this is similar, but then your entangling gates, or your 2-qubit gates, can only be between neighboring qubits and not between any 2 qubits. So let's move over to the coding notebook to try it out. Okay, so first import the libraries that we need. And then the goal in VQE is to iteratively update a trial wave function based on some measured expectation value. And in typical VQE, we're seeking to minimize the expectation value of the energy, and minimizing that gives us a good approximation for the ground state energy. And we can also apply these same ideas to other situations. So for instance, our goal could be to apply an Rx rotation and have the average measured state of the qubit be 1/2. In other words, we should measure approximately 0 50% of the time and 1 50% of the time. And we know that this happens when our state vector lies on the equator of the Bloch sphere. So we know that the angle that we should rotate by is 90 degrees, rotating from the 0 state to the equator. So first we can create our variational circuit, which has an angle as a parameter. Here I'm just converting, if the angle happens to be a list instead of just a number, then take the first element of the list. This is just so it works with our SciPy optimizer later. So we want to do an Rx rotation of our given angle on our 0 qubit. Now we need to define the cost function, so the thing that tells us how good or bad our expectation value is. So first we're going to use our variational circuit with our parameter angle. We're going to run it and get some counts, and then we're going to compute the cost. And we're just going to do the squared error between the current and desired expectation value. So the average qubit state is going to be the number of counts that were 1, and if there was none, default to it being 0, divided by the number of shots. And what we really want is 1/2, and we're just going to square this difference and return the average cost here. Now we're going to repeat this over and over and minimize with a classical optimizer. So we're going to have some initial guess. Here I've picked 30 degrees. And we're going to use SciPy minimize to minimize our cost function, starting with our initial guess, and then get the best angle as a result. So let's see what happens. And our optimized angle in degrees is 90.76, which is pretty much right what we were looking for. If you run this other times, you'll get other results, but it's pretty close to what we want. You're going to also change the target. So for instance, if you wanted this to be 0.25 instead, then the optimal angle is going to be something different. So you can play around with that if you're interested. And then here's a challenge problem, which is to apply the same approach as above, but for 2 angles that are your parameters. So the target is to end in a specific state rather than just be on the equator. So now we can think about another situation, which is also a relatively simple example, which is an electron in a magnetic field. So the Hamiltonian for an electron in a magnetic field in the z direction is just sigma z. And here I've ignored the magnitude of the magnetic field and it's just sigma z. And sigma z is a Pauli matrix. Before in the course we've also used the notation capital Z, capital X and Y. And the 2 eigenstates of the electron are spin up and spin down. And the lower energy state is going to be spin up since the electron spin is aligned with the magnetic field. And we can map that to 0 on our quantum computer. And the higher energy state is spin down. That's a typo here. Since the electron is anti-aligned with the field. And we can map that to 1 in our quantum computer. So now suppose that we turn on a magnetic field in the x direction with equal strength to the z direction. So now our Hamiltonian is going to be sigma x plus sigma z. And we want to apply VQE to find the ground state energy of this Hamiltonian. So the first thing we can do is define our Pauli operators. So this is just what the Pauli operators are, and then our Hamiltonian is going to be sigma x plus sigma z. And then we can see what the eigenvectors and eigenenergies of the system are. We just solve for the eigenvalues and eigenvectors and print them out. Our two eigenvalues are plus and minus 1.414, which is plus or minus root 2. And these are our two eigenvectors. And these are going to be antipodal on the block sphere, so pointing in exact opposite directions because they're orthogonal to each other. So we can also print out where these lie on the block sphere. So we know that this coefficient in front of the 0 state, if we write it in terms of the angles on the block sphere, the polar angle theta down from the z-axis, and phi is the azimuthal angle from the x-axis, then this value should be cosine of theta over 2. So we can write this as 2 times the arc cosine of that coefficient. And then the other one is going to be antipodal to that. So it's going to be angle 1 plus pi, or plus 180. Oops. Sorry, for us is in radians, plus pi. Okay, so the angle of the first eigenstate is 45 degrees and the angle of the second one is 225 degrees. And we know that the second eigenstate has the lowest energy. So the second eigenstate, basically we know that this angle, 225 degrees, is what we should expect to get from our variational circuit. So in order to find the expectation value of the Hamiltonian, we need to know is the linear combination of the expectation value of sigma x and the expectation value of sigma z. So we need to be able to measure both in the x basis and in the z basis. So here's our quantum circuit. We're going to apply an Ry rotation this time because we want to apply an Ry rotation because these eigenstates should lie in the xz plane. And then if we want to measure in the x basis rather than the z basis, all we need to do is apply a Hadamard gate before we measure. And this rotates the x-axis onto the z-axis. So when you measure, if you measure 0, that's actually the same as measuring plus. If you measure 1, that's the same as measuring minus. So now we have to define our cost function. We want to compute the expected value of h, so we need to compute the expected values of sigma x and sigma z. We need to convert our counts, which are the number of times we measured 0 and the number of times we measured 1, into those Pauli operator expectation values. And those eigenvalues of the operators are plus or minus 1. So if we apply this conversion, we can get the expectation value of our Pauli operators. So the first thing that we're going to do is we're going to measure in the z basis for some number of shots, and then we're going to get the probability of measuring 1, and then the expected value of z is going to be 1 minus 2 times the probability of measuring 1. Then we want to measure in the x basis, so same exact thing, but now measuring in the x basis. And here again, we're just going to have 1 minus 2 times P1x. And then the average cost is going to be expectation of sigma x plus expectation of sigma z, because that's expectation of h. And now we can have our initial guess. So pick your favorite. Maybe let's do 70 degrees. And our optimized angle is 227. Compare that to what we were hoping for, which is 225, and that's pretty much on the money. We can check the ground state energy that we got as well. So rotation Ry of theta can also be expressed as e to the minus I sigma y times theta over 2. And so if we write this out, that's the matrix in the exponent. Ry is the matrix exponential, which is different than exponentiating each element of the matrix separately. Matrix exponentiation, remember, you can think of it in terms of a Taylor expansion. So it's a linear combination of different powers of that matrix. And then that eigenvector is going to be Ry times the 0 state, because that's what we started in. And then the ground state energy is just going to be the expectation value, or our approximation for the ground state energy is going to be the expectation value of H. Oops. For doing matrix multiplication, don't use the times, use an at. Okay, and we got minus 1.412, which is pretty close to what we were expecting, 1.414. So a challenge problem that you could try is the case where we don't have the magnetic field equally balanced between the x and z directions. Try this out and see if you can also get the right ground state energy. Lastly, let's use a real-world example. So a molecule of hydrogen gas has a ground state energy of minus 1.173 Hartree, which is 31.9 electron volts if you prefer those units. And that's for an atomic distance of 0.735 angstroms. And we can use VQE to find this. And here we're actually going to just use the built-in VQE functions. So both the Ansatz preparation and the optimization. So here are some examples. So we can have hardware efficient Ansatz using the SU2 approach. And we're going to do that for 2 qubits with full entanglement between the qubits. It will look like this. So basically we've parameterized our theta to be 12 different angles. And then when we do the VQE, we're going to optimize and find the ideal vector theta to give us our ground state energy. We could also do a chemically inspired Ansatz, which is called the unitary coupled cluster type. And that one looks a little bit different. And we call this the 2 local because only nearest neighbor qubits are going to have entangling gates between them. So now we can build our Hamiltonian. So basically, this is what it is. So it's a 2-qubit Hamiltonian. So there's a term that's sigma z on the first qubit times the identity on the second. There's a term that's sigma, or identity on the first qubit and sigma z on the second qubit. We also have these cross terms, which is sigma z on the first qubit times sigma z on the second qubit. And then each of these elements in the Hamiltonian has some coefficient associated with it. And you can use a sparse polyap function to build your Hamiltonian out of that. And then finally, we can try it out. So we pick our Ansatz type, we pick our optimizer type, and then we run VQE. And then this estimator here, is coming from the Quantum Rings Qiskit toolkit up here. So we can run it, compute the minimum eigenvalue, and we get minus 1.173 Hartree, which is super close. It's basically spot on for what we expected. I hope you liked seeing a little bit of what we can do in our NISQ-era with the Variational Quantum Eigensolver. And next week, we're going to be talking about a different variational algorithm, which is the Quantum Approximate Optimization algorithm. I'll see you then.